Now that we've practiced finding sine, cosine, and tangent for different angles using their reference angle, we move on to a series of 3 sections. So today's 19.1a. So today we're graphing y equals sine of x. On your circle that you've been practicing, so on the xy coordinate plane where you've been graphing them, remember that a quarter of the way around a circle is 90 degrees. Halfway around the circle is 180 degrees. 3/4 of the way around the circle would be 270 degrees. And then to get back where you started, that would be 360 degrees. Every time sine goes around the circle, it starts over again. And so you're looking at the different values of sine kind of as you go around. There are some values of sine that are decimals, and so we'll definitely get examples of those as we're doing this today. But these are the values of sine where they have different answers, is one way to think about it. So on the interval from 0 to 2 pi, sine has different stuff happening. And then when it comes back around, it starts over again after 2 pi. But we could graph these to see what's happening at these different places. So let's see. So the sine of 0, we're working in radians actually. So let's make sure that our calculator is in radian mode. If it's not in radian mode, remember how you can fix that. So you can do mode, go down to the 4th option, and then come over to where it says radian and degree, and you can switch it back to radian. You can also remember that resetting your calculator will always put it back in radian mode. So I'm working in radians right now. So the sine of 0 radians, or 0 degrees, is 0. So at 0, sine is 0. Remember, I'm working in radians. The sine of pi over 2, which is the same as the sine of 90, is 1. The sine of pi radians, which is the same as the sine of 180 degrees, goes back to 0. The sine of 3 pi over 2 radians, which is the same as the sine of 270 degrees, that one gives me -1. And then when I go back to 2 pi, it's going to give me the same thing that I got at 0. Sine of 2 pi radians, oops, try that again. The sine of 2 pi radians gives me 0 again. And then after that, the cycle would just continue. So for sine, this is the graph of y equals sine of x. So 0 goes with 0. Pi over 2, oh, so we should talk about that. So on this scale over here, these count as 1. So this is 1, 2, 3, and -1, -2, -3. But coming this way, this is pi over 2, and then this is pi, and this is 3 pi over 2, and this is 2 pi. And then coming this way, it's the same thing, but it's just the opposite. So this would be -pi over 2, and then -pi, and -3 pi over 2, and -2 pi. So when I graph sine on one of these special graphs, 0 goes with 0, pi over 2 goes with 1, pi goes with 0, -pi over 2 goes with 3 pi over 2 goes with -1, and then 2 pi goes back with 0. And so it creates this wave. It kind of looks like a sound wave. If I kept going on the negative side, the pattern would continue, but it would continue based on the pattern. And so I could plug these into my calculator too to make sure I'm getting the right answer for the question. The sine of -pi over 2 would be -1. The sine of -pi would be 0. The sine of -3 pi over 2 would be up here at +1. And then the sine of -2 pi would be back to 0. And again, you can plug those into your calculator to confirm that they're correct. So what ends up happening is when you graph these, and I'm going to do it in pencil to make sure I don't mess up, it creates this undulating pattern of a wave that repeats itself. And then I make sure that I put arrows on the end to indicate that it keeps going. So this is called the sine curve. So it's repeated cycles that form this wave-like shape. Because it repeats itself every 2 pi, we say that this is periodic. And so one thing that you want to label when you're doing this is you want to label what's called the period of sine. So you can pick any 2 points where it's either at its highest point or pick any 2 points where it's at its lowest point. You can also go from 0 to 2 pi if you want to label it that way as well. But so the period tells you when does it restart. So how long does it take to get back to the same place where it started? And so again, you're just measuring from any 2 equal distances on the graph. So let's say you pick the 2 high points. – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – –– – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – –– – –– –– – – – –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– –– ––– –– –– –––– –– – – it takes until pi over 2 to get back up to the same place. Again, you could go from here to here, or you could go from here to here. You're measuring the same thing on all of them. So for this graph, the period of this graph, we label as 2 pi radians. So it takes 2 pi to get back to where it's going. There's other things that we can measure as well on this graph. And so for this one, we can also measure the graph's amplitude. Amplitude is defined as being how far the graph rises above the midline. And so for this one, it goes up to +1 and it goes down to -1. So when you measure amplitude, you're measuring either this distance here on the top or you're measuring this distance on the bottom, and it's going to be the same thing. So for this one, I'll label it here. I should use a different color though. I'll use blue. So for this one, the amplitude is this distance right here. So I'm just going to color it in blue so you know what I'm measuring. And I'll make a little line over here. So for this one, the amplitude on the graph is +1 because it's going up 1 or it's going down 1 from that x-axis. Before we move on to graphing the transformations of the sine function, there's a couple things about this picture that I want to make sure to talk about. Sine always goes through 0, and that's important because the graph of cosine that we're going to talk about tomorrow looks a lot like the graph of sine. In fact, it's almost identical. The only thing that's different is that the cosine of 0 isn't 0. So anytime you see one of these graphs go through 0, 0 right here, that's going to be part of your reminder that you know that this is a sine graph. What we're going to continue with now is transformations of these functions. It says, like all other types of functions, the sine function can be shifted, stretched, compressed, and reflected. So we're going to be looking at specifically stretches and compressions of the sine function. So in example number 1, we're still graphing y equals sine of x. The only thing that's different about it is that it's stretching by 3. And so when you perform a stretch, then let's a couple of things. So the 3 is out front, which means it's going to stretch everything up to be either 3 times as tall or 3 times as, not tall, under. 3 times, it's going to be 3 times further away from the x-axis than it was when we started. So let's make a note on this one that it's a vertical stretch times 3. So it's going to be 3 times as curvy, if you want to think about it that way. Let's see. So we're basing everything off of this table that we did before. So sine of 0 is still 0 because 0 times 3 is still 0. But then here's where it changes. This was pi over 2. Oh, we should label these. Pi over 2, pi, 3 pi over 2, and 2 pi. Negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. So you do always want to label those. These ones you can just leave not marked because we assume that they're 1 unless otherwise stated. Okay. So sine of 0 is 0. Sine of pi is 0 because 0 times 3 would still give you 0. And then sine of 2 pi gives you 0 because 0 times 3 would still give you 0. And then over here, this one's going to stay at 0, and this one's going to stay at 0. So those numbers aren't changing. What's changing is this 3 that's out front. And so that's going to make, instead of pi over 2 going with 1 like it did on the last part over here, pi over 2 isn't going to go with 1. It's going to come all the way up, and it's going to go to 3. So it's going to stretch it 3 times as tall. And then this one is going to go down to negative 3. So it's going to stretch it 3 times under, up and then down. So this one's down. So this one won't go to -1. It'll go to -3. And then this one won't go to +1. It'll go to +3. So a vertical stretch by 3, you know it's a vertical stretch because it's on the outside. And I always draw these in pencil because I usually mess up. So what it changes is it changes the amplitude of the graph. A vertical stretch is always going to change amplitude. The period of this graph is still the same. Remember, with period, you can count it from any 2 points that are on the graph that are in the same place. So if you wanted to, you could count the period down here from lowest to lowest, or you could count it up here from highest to highest. It doesn't matter. So for this graph, the period, or the time it takes it to repeat, goes from negative pi over 2 to positive 3 pi over 2. So the period for this graph is still going to be 2 pi. What the vertical stretch changed, though, was the amplitude. Remember, the amplitude is the distance from the tallest part from the midline to the tallest, or from the midline to the lowest part on the graph. So if I labeled period right here, usually it's labeled with a dashed line, but I'm color coding it, so I'm just going to have it be labeled with a solid line because it's colored. So this distance right here for this graph, the amplitude is 3 because it's stretching it so that it goes up 3 instead of just going up 1. My next graph on B is also going to be a vertical stretch. So this one's going to be a vertical stretch times 2. But it's also going to be a reflection. And so that negative out front is going to flip the graph so that it goes the opposite direction than it normally does. When I'm putting my points on this graph, though, here, let's label these. Pi over 2 pi. Okay. So let's see. A vertical stretch times 2 and a reflection. But 0 still goes with 0 because 0 times 2 is 0, and then flipped it's still 0. This one with pi still goes with 0 because the sine of pi is 0. This one still goes with 0. So a vertical stretch doesn't change a 0, and a reflection doesn't change a 0. So those ones stay in the same place. The only time that they'll move is for a horizontal stretch or compression, and we'll look at that in just a second on the next one. So normally, pi over 2 for sine goes to positive 1. A vertical stretch means that it would be going up to positive 2, but a reflection means that it wouldn't be going up to positive 2, it would be going down to negative 2. So it makes it go the opposite way. Instead of coming up from here, it's coming down from here. So normally the pattern is it goes 0, 1, 0, negative, 1, 0. So when it goes 0 and then down negative, you know that that means that there was a reflection. This one would get stretched up to positive 2 instead of down to negative 2. This one would get stretched up to positive 2 instead of down to negative 2. And then this one would get stretched down to negative 2 instead of up to positive 2. It doesn't seem super important today because we've only learned about, that one's a little low. We've only learned about this one type of graph so far, but after we talk about cosine tomorrow, it's going to be really important that you notice, and I didn't label it on the last graph, so I'm going to go back and label it. So because this goes through the point 0, 0, that's how you know that it's a sine graph. Same thing on this one. Because it goes through the point 0, 0, that's how you know that it's a sine graph. If it was going through any other point besides the number 0, then it's going to be a cosine graph if it has this same shape. We're going to label the period, and we're going to label the amplitude. So for this one, for it to get back up to where it goes, and you can pick any 2 points on the graph, they're going to be the same distance apart because of this repeating pattern. So for this one, the period is also 2 pi. Vertical stretches or compressions don't change the period of a graph, but they do change the amplitude of a graph. So for this one, where's a nice place to label it? I'm going to label it right here. The amplitude's always positive, but it doesn't matter whether you're counting up or whether you're counting down, but it's just this vertical distance right here. And so for this one, the amplitude for my graph is going to be the number positive 2 because it's stretching it up 2 instead of stretching it up 1. So for question C, it's a little bit different. Notice that the 2 on this one is on the inside of these parentheses. It's not on the outside like these numbers were on the previous 2 problems. And so that's important because that means that this is not a vertical stretch or a vertical compression. When the 2 is on the inside, it means that it is a horizontal, and then inside's opposite. Normally 2 would mean stretch, but because it's on the inside, it's a horizontal compression by a factor of 1/2. And so inside is opposite, so it's flipping. That means that it's going to be compressing horizontally, so it's going to be squishing in this way. When we label our graph for this one, anytime you have a horizontal stretch or a horizontal compression, it means the zeros are going to be happening at different places. So 0 still goes with 0. That part doesn't change. That part's like the middle of your graph, so that point is going to stay consistent for any sine function. But here's where it's different. Normally, my zeros go here, and my zeros go here. So what's going to happen is, instead of the graph coming back to 0 at pi, and then coming back to 0 at 2 pi, the graph's going to come back to 0 faster than that. So when it compresses by 1/2, instead of going back to 0 here, it gets back to 0 twice as fast. So that means it gets back to 0 here. Instead of getting back to 0 here, that means that it gets back to 0 here. Remember with sine, the pattern is 0, +1, 0, -1, back to 0, and then that pattern would continue. So that would mean it's going to get back to 0 here, and it's going to get back to 0 here, and then it's going to get back to 0 here and here. That's squished in by half, and then it'll happen again here and here. So for these graphs, what you have to figure out is sort of what happens in between. There's no reflection, so it's not flipped upside down. There's no vertical stretch. There's no number out front, so it's not getting any taller, which means all of this is going to happen between +1 and -1. So the pattern for sine goes 0, +1, 0, -1, 0, and then it repeats itself. So 0, 0, which means it has to get up to +1 halfway in between these. So at pi/4, it gets up to 0, and then 0, and then at -1, so that's halfway in between these, and then back to 0. What's happening is the period of this graph is being shortened up because it's a horizontal compression. 0, +1, 0, -1, back to 0. And then the pattern would continue over here. So down to -1, back to 0, up to +1. And this up to +1 is happening exactly halfway in between these 2 points. Down to -1 is happening exactly between these 2 points. And then back up to +1. So when I draw in the sine curve for this one, it's not like the waves aren't bigger, they're just happening more frequently. The amplitude on this, so that distance here that I've been marking in blue so far, my amplitude for this one is still +1. So horizontal compression doesn't change the amplitude on a graph, but what it does change is it changes the period. Remember that to find the period, you're going to find 2 points on the graph that are at the same place, and then you're going to figure out how far apart from each other those are. This is halfway in between 0 and pi/2, so this is pi/4. And then this is halfway in between pi and 3 pi/2, so this is at 5 pi/4. So what happened is it's repeating, that's not how you spell period, it's repeating itself twice as fast, which means that the period is half as long. So normally the period would be 2 pi, but when it squishes this way, it goes up, down, back up, and it only takes half the normal time that it does to complete each wave for the graph. So horizontal stretches and compressions will affect the period, whereas vertical stretches and compressions affect the amplitude of the graph. The last example for today, say to write an equation for the graph, there's a couple of things that you want to notice about this one before you start. Remember, anytime the graph goes through 0, 0, you know that's how it's going to be a sine function. So for this one, as soon as you see that point right there goes through 0, 0, that's your clue that this is going to be sine and not cosine. There's a couple of other things that you want to notice about this graph before you start writing down numbers. I always like to put the points on the graph, even if it's missing those things. So the zeros and then the high and the low, but just because it helps me start to see how long it takes for the graph to repeat or to go through like one revolution or one rotation. So the period on this graph has been affected and the amplitude on this graph has been affected. And then there's also one other thing about it that's different. The normal pattern for sine goes 0 up to +1, back to 0, down to -1, and then back to +1. And so because of that, you may make a note somewhere on here that because it goes from 0 and then down, that means that there was a reflection that happened with this graph. So that's going to be one of the things that we need to notice when we write the equation for the graph. The next thing is the amplitude is different. Amplitude is the vertical distance between the highest or lowest point on the graph and the midline. And so for this one, the amplitude is 3. Remember, it's measuring that distance right there. So that means that there's a vertical stretch times 3. So we're going to need a 3 out front along with that negative. And then the last thing that you want to notice is the period on the graph. And this is always the hardest part for students to see. Period's the amount of time it takes to get back to where it started. And you can measure it from anywhere. So if here, this is at pi/4, and then here, this is at 5 pi/4, the period of this graph is pi, but the normal period for a sine curve is 2 pi. That means that it's been compressed this way by a half. So in addition to the things that I've mentioned so far, there's also a horizontal compression times 1/2. And sorry, that's a little bit hard to see with the way that I wrote it. There, that makes it a little bit more clear. So when I write my equation for this one, it goes through 0, 0, so I know it's a sine graph. There's a reflection, there's a vertical stretch times 3, and there's a horizontal compression. So my answer for this question is going to have a lot of parts to it. I'm going to write it down here. Y equals, because I'm writing an equation, I know it's going to be sine. The reflection means that there's a negative out front. The vertical stretch, because the amplitude changed, means that there's going to be a 3 out here. I know it's sine because it went through 0, 0. And then on the inside of the parentheses, it was a horizontal compression by a half, and so I'm going to need a 2 along with the x on the inside of the parentheses. And so all of these things would combine to give me the equation for what this sine graph would have been produced from.